Today, I'll be taking us through what we call HESS law. That is heat of constant formation. I'll be taking us through HESS law. Um, okay, HESS law. So that is HESS law of constant heat formation. But the question is simple. So what is HESS law? Before we try to look at what HESS law is, it's important for us to know that HESS law is a very important product or outcome of the first law of thermodynamics. Recall that we had discussed something regarding thermodynamics in our earlier classes when we talk of exothermic and endothermic reactions. So Hess law is an outcome, very important outcome of the first law of thermodynamics. So it stands to approve of the content of the first law of thermodynamics. So you see that first law of thermodynamics, of course, it deals with heat, energy, and work, a relationship between them. So believes that work is done when there is an internal energy that it's actually affected by the presence of heat. So from what we know, we already know that the first law of thermodynamics simply explains the fact that energy cannot be created, cannot be destroyed, but can only be transformed from one form of it to the other. So Hess law is that particular part of thermodynamics or thermochemistry that affirm that particular theory of the first law of thermodynamics. But Hess law itself, simply put, heat of constant formation, says that wherever there is heat changes for any sort of a reaction, an overall reaction, that the heat change for that overall reaction can be obtained from a summation of the individual heat changes of every step that leads to the product. So enthalpy changes or heat changes for any process, whether it's a physical or chemical process, is the same irrespective of the number of steps that is being taken for the product to be obtained. So if you have, for example, if we have A to B to C to D and back to B, and this is our enthalpy change or heat change, and this is our heat change 1, and this is our heat change 2, and this is our heat change 3. What Hess law is saying is this, that the heat change, for example, the overall heat change, let us use arrow, for a particular reaction A to B, for A to B, can be, let's say, minus delta H 321.1 kilocalorie per mole, and that even if this reaction decides to use these several steps to get to the product, that is to say, if the reaction A to C, if the reaction, let's say reaction AC, the change in enthalpy 1 is, let's say, 200 kilocalorie, and then the reaction CD, the change in enthalpy, let's say it's 100, and then we also have the reaction DB. Let's say the change in enthalpy is for 3 is 21.1. So what Hell's law is telling us is simple. It's saying that, look, even if this reaction decides to take these several parts to get to the product, the enthalpy change, the heat of formation of this product will still remain the same, even if it goes this long way. So to it means that this will be AC plus CD plus DB. And if that is the case, it means that delta H of 1 plus delta H of 2 plus delta H of 3 will give us what? 200 plus 100 plus 21.1, and this will still give us 321.1 kilocalorie. So Hess law is saying, look, irrespective of the several steps that it takes to get to a reaction, to get to a certain product, whether it's a physical or chemical process, the heat change, the total heat change for that reaction remains the same. Now, with this, we can brace ourselves with something very important, and that is the fact that the Hess law believes that enthalpy is a state function. It's a state function. Remember that when we said a particular thermodynamic property is a state function, it means that it is independent of what the path that is taken to arrive at a particular product. Instead, it is interested at that particular state at that moment to which the reaction gets to the product. That is what we mean by state function. So, with Hess law, it has also affirmed the fact that enthalpy, which is a heat change, is also what? A state function. And like I said, as a state function, it is independent of what? The path to which the reaction takes to get to the product. Instead, it is interested only in what? That state at that moment to which the reaction formed to get to the product. So with Hess law, two things are pertinent. Hess law affirms the fact that the first law of thermodynamics is actually dependent upon the fact that heat cannot be created or be destroyed, but there's a transformation in the process. And also affirming the fact that the first law of thermodynamics, which is based on enthalpy changes, is what? A state function. Now, let us take an example and see how we can probably solve a problem using Hess law. Let's see how we can solve a problem using Hess law here. Let us look at the formation. Let us look at the formation of sulfur trioxide gas from sulfur. The formation of sulfur trioxide gas from sulfur. Now, you know that you can ordinarily react sulfur with oxygen, depending on the number of moles of oxygen, and you can get sulfur trioxide gas. But you can also follow the different steps of the formation of sulfur trioxide to arrive at sulfur trioxide. Now, in that case, there is a different heat change for every process. Now, if we follow that, the first one is going to be the formation of sulfur dioxide. That is going to be the first one. The formation of sulfur dioxide. That will be the first part of it before we get to there. So the formation of sulfur dioxide will be sulfur plus oxygen, and this will give us sulfur dioxide gas. Now, this can have an enthalpy change of, let's say, let's just take an instance and say, okay, 20.1 kilocalorie per mole. Okay, that is the first heat change for the first step to arriving at what? At sulfur trioxide. Now, the second step is going to be the conversion of the sulfur dioxide to what? Sulfur trioxide. Now, so the second step will be the conversion to what? To sulfur trioxide gas. That means we'll now have here sulfur dioxide gas plus plus what? Plus a half of oxygen, and that will give us sulfur trioxide gas. Now, of course, this comes with its own heat change. Let's say its own heat change is 10.2 kilocalorie per mole. Okay, you can see that from here, the first step, there is a heat change. In the second step, there's a heat change. So the net reaction, um, will now be this and this. So we have sulfur plus oxygen to give us SO2 gas, and then we also have SO2 gas plus half O2 to give us SO3 gas. So with this, we can possibly, of course, this can cross this, okay, and then we can have a net reaction. In this format. So we can have sulfur, okay, plus 3/2 of oxygen to give us SO3 gas. You see, this will have an enthalpy change, which is going to be the overall enthalpy change. That is going to be the addition or the summation of this and this. So if we add minus 20.1 kilocalorie per mole plus minus 10.23 this, we are going to have minus 30.3 kilocalorie per mole. With this, it shows us that HESS law actually is saying the truth to the fact that irrespective of the steps that you take to arrive at a particular product, be it a physical or chemical process, it does not matter the heat changes that will arrive at the end of the day. The heat change, the total overall heat change will remain the same. So it means that even if we had reacted sulfur directly with oxygen this way, we will have obtained sulfur trioxide. Now let us look at what that means using the HESS law diagram. Now from the HESS law diagram, what that means is that from the HESS law diagram, what that means is that we can possibly have our first reaction, which is the initial, which is this, which is S plus 3/2 oxygen arriving at SO3 gas. Can have that, and we can also pass through the various steps where sulfur plus oxygen 2 will give us SO2 gas, which is the first, one of the steps. Or we can possibly pass through where we have sulfur dioxide plus this to give us sulfur trioxide gas. So, okay, so if you see this, you find out that one will have ordinarily expect, and this is delta H2, one will have ordinarily expect that we react this directly and get sulfur. That even if we do this, we are still going to have an enthalpy change, overall enthalpy change of minus 30.3 kilocalorie per mole. But if we choose to use through here, we'll definitely be having our enthalpy change here, which is minus 20.1 kilocalorie per mole, and then here we'll have minus 10.1 kilocalorie per mole, which means that by HESS law description, it doesn't matter the path to which the reaction is using, but at the end of the day, the summation of the individual heat changes in the course of the step of the reaction will always give you the same total or overall enthalpy changes. So with Hess law, it is strongly believed that the first law of thermodynamics, which depends seriously on enthalpy of a reaction, which is the heat change of a reaction, is what? Is a state function. So it does not depend on the path to which the reaction is taken, it only depends on what the state at the moment to which that reaction is taken. And the state at the moment could be temperature, could be pressure, could be volume that is influencing it. Today, I'm sure we've learned something good again on that thermodynamics, which is what? Hess law. I will encourage us to always listen to these videos, watch these videos, and please do not forget to subscribe, do not forget to like, do not also forget to follow, to share. I am